So as we said, the second step is allocation sequence concealment. As we said, it is essential that when a person is recruited into a study, no one can predict which group that they will be allocated to. And this is important because it prevents knowledge of the next allocation from changing the order or whether somebody gets involved or not into a trial. And I'm just going to take a slight second here to re-emphasize a point that it's really important not to confuse allocation concealment from blinding. So allocation concealment protects the allocation sequence before and until allocation. And it should be possible to successfully implement this no matter what your interventions are. On the other hand, blinding, which will be covered in subsequent sessions, seeks to prevent bias subsequent to randomization by continuing the concealment of the assigned intervention after randomization. And blinding can reduce the risk of bias due to deviation from the intended intervention and bias in the measurement of the outcome depending on who is blinded. Blinding after randomization cannot always occur. For example, it may be impossible to blind participants in trials comparing surgical with non-surgical interventions, but it is possible to conceal the allocation in those trials. So I hope that really is clear, and that you can distinguish between allocation concealment and blinding. So adequate methods of allocation sequence concealment result in an allocation sequence, which is, an allocation which is not foreseeable. And the most desirable way to do this is through central randomization by a third party. So with some sort of central allocation, you might be able to access it by the phone or over the web, or it might be based in a pharmacy. There are other adequate methods, such as sequential numbered sealed opaque envelopes or identical drug containers. But with these techniques, it's really important that all of the safeguards are in place. So as I said, with the envelopes, it's really important that they're numbered, sealed, opaque, that the envelopes are opened sequentially, and only after the envelope has been irreversibly assigned to a participant. And there's quite a lot of evidence that even when if these checks aren't all in place, that there seems to be some susceptibility to manipulation. And as we said, inadequate methods of allocation concealment mean that people can foresee what future allocations will be. So this is obviously, if the randomization sequence is known to staff in advance, that's obviously a big problem. If, as we mentioned, the envelopes or the drug containers don't have all of the safeguards, that can be a problem. There's also can be the ability to predict assignments successfully based on previous assignments in blocked randomization with a fixed block size. So this can occur if you have a trial where the intervention can't be blinded. So the assignments are known after enrollment, and if you have a single centre and you've managed to deduce what the block size is. If, for example, let's say the block size was 6, you know how 5 participants were, what intervention group they were allocated to. It is possible to deduce the last allocation for the 6th person. And then finally, obviously, if you have a non-random or some sort of systematic allocation sequence, then it's really difficult to conceal it because it can be predicted. Now, I think I made a big point there about needing all of the safeguards with the envelopes and with the drug containers, and you may find it hard to believe that personnel involved in trials may want to subvert randomization, but there are quite a few examples of this happening, and just this is from an admittedly old paper, a 1995 paper by Kenneth Schultz, where he reports on his experience during epidemiology workshops, where he asked medical residents and medical school junior faculty if any of them had deciphered or had witnessed someone else decipher an assignment sequence. And more than half of the participants could describe at least one incident of this happening. And there were many different accounts of how this happened, including taking advantage of posting of the allocation sequence on bulletin boards, a lot of examples to do with envelopes, so opening unsealed envelopes, holding translucent envelopes up to the light, feeling, if depending on what's in the envelope, if there's a difference in the weight of the envelopes, opening unnumbered envelopes until the desired treatment was found. I mean, people were being quite inventive about how they were going to deduce the randomization sequence, or basically from the experience of the appearance of tablets or labels on the drug containers. And I mean, why might people want to do this? And I think generally people aren't concerned. They're not doing this to really ruin the trial, but it's because they either think that they know what the more effective treatment is, and they want the results of the studies to reveal what they believe to be valid, but also because they want to generally do the best for their patients. And if they believe that the new treatment might offer benefit, they really want to do anything that they can to make sure that their patient gets that treatment. So hopefully you appreciate that that generating a randomization sequence and then really doing your best to conceal it is really important. Now, the final thing that we're just going to cover in this part of the presentation is about evidence of problems that have occurred during the randomization process from baseline imbalances. So there have been arguments that risk of bias assessments should consider where the participant groups are balanced at baseline, as this could indicate that something may have gone awry during the randomization process. But what we're looking for here are problems that are clearly beyond what would be expected due to chance, not slight imbalances. So the sort of things that we're looking for, which might suggest that there was a problem during randomization, are substantial differences between intervention group sizes compared with the intended allocation ratio. So if you're expecting a 1-to-1 ratio and it really differs from that, then that might be a cause for concern. But obviously, it really depends on the method of randomization used and the size of the trial, what you think. But these are differences which you really can't put down to chance. Another thing that might be a cause for concern is a substantial excess in statistically significant differences in baseline characteristics between the intervention groups, again, beyond what would be expected by chance, or imbalance in key prognostic factors, again, that are unlikely to be due to chance. So I'm just going to repeat again, this is not a few instances of p less than 0.05. This is really what we're looking for here is clear differences that are really unlikely to have occurred by chance. And another thing to mention is, although I'm telling you about looking at baseline imbalances, it might also be a cause for concern if there's excessive similarity in baseline characteristics between groups, which again is not compatible with chance. So for example, if you have a small trial which did not use any form of randomization which you might expect to lead to balanced groups. So for example, let's say it used simple randomization, simple unrestricted randomization, and yet there are no differences at all in baseline characteristics. You might wonder how that had occurred. So just to again try and emphasize the difference between things which can happen by chance and the things which might be suggestive of problems during the randomization process. Just got a quick question for you. If 20 variables are measured at baseline, would you expect at least one variable to have an imbalance leading to a p-value less than 0.05? So the majority of you got the right answer. Yes, so 83% of you said yes. And if we assume that the variables measured are completely uncorrelated with each other, i.e. there's no, one of them doesn't affect the other, they're completely unrelated, a p-value less than 0.05, you would expect 1 in 20 tests to have that. But you could see more, still compatible with chance, if factors are correlated with each other. So for example, if you have a chance imbalance in age, and age is correlated with other factors or associated with other factors, it may lead to imbalances in those as well. And even if you saw no imbalances or a lot of p-values less than 0.05, it's still quite difficult to interpret what exactly this means, because it is possible that trial investigators select the tests for baseline imbalances that are reported, either because they are statistically significant, have this p-value less than 0.05, or because they are not. So just trying to reinforce that you would expect in any, most tables of baseline characteristics measure, are reporting at least 20 variables often, and you would expect to see some p-values less than 0.05, and this is not a cause for concern, this is just chance. And you also have to bear in mind that it has been argued quite strongly that statistical tests for differences in baseline characteristics should not be used in randomized controlled trials, because in theory, the null hypothesis that there are no systematic differences between intervention groups is known to be true. So it is actually almost also unlikely that you will see p-values in the tables of baseline characteristics. And what we're really looking for is differences which are so extreme that they are jumping out at you without you having to test them for statistical significance. Okay, so we've got another little example for you, and if you have downloaded the handout, this is in the handout, but I'm going to ask you a little question about this this trial in a minute. But just to give you some background, this is a 1948 trial comparing anticoagulation medication to conventional treatment for a heart attack, and the drug that people were received depended on whether they were admitted on odd or even days, and those admitted on odd days received the new treatment, so with an anticoagulant, and those admitted on even days got the conventional treatment. And the desired allocation ratio was 1:1. But as you can see here, there were 589 patients in the anticoagulant group and 442 patients in the conventional treatment group. So what I would like you to think about is, what do you think that the likely reason for these unbalanced numbers is? So I'm going to, in a second, we're going to go on to a poll and give you some options, but just whilst we've got this slide up, if you just want to think about, do you think that these differences were due to chance? Do you think that it's possible that more even days fell on weekends when recruiters were absent? Do you think that investigators failed to enrol eligible participants on even days because they wanted to give them the new drug? Or do you think that the enrolment schedule wasn't strictly adhered to? So we don't know for sure, and so I can't say that any of you have the right answer or not the right answer, but just to let you know, so 16% people said chance, and that is a possible explanation, but here the p-value is for this group difference is quite small, so it is possible, but it seems unlikely. Quite a few people thought that more even dates fell on weekends. Around 30% of you thought that. And again, it's possible, but if we assume that the trial recruitment occurred over a period of several weeks, we would hope that the days falling on weekends ends up being balanced. So we think that that is unlikely. And then the two letter options are basically saying the same thing. So 20%, 28% of you said that the enrolment schedule wasn't strictly adhered to, and 25% thought that they didn't enroll eligible participants on even days. And I agree with both of those, because I think that there's the suspicion that the investigators manipulated the allocation so that more patients were recruited on odd days when they would receive the new anticoagulant. But as I said, this is just a judgment, and it's kind of also informed by the fact that in this trial, it's clear that an inadequate method of allocation was used. You know, this odd versus even dates, definitely a deducible allocation sequence. So I would be concerned in this case. But there are other examples where it seems that adequate methods for randomization were used and trials still end up with large differences in group sizes. So this is an example found by Julian, of a trial of a pre-dive checklist. So this is for scuba diving, and despite so they randomized in a 1-to-1 ratio, but again we have 693 people allocated to the pre-dive checklist and 467 allocated to the control group. And this is despite, as I said, sort of solid methods being described. So it says that the allocation was concealed, and that and it seems that all of the methods were followed. So the reason for this discrepancy in group sizes is unknown, but concerning because it is really quite large difference in group size. Okay, so I've come to the end of the sort of theoretical underpinnings of bias arising from the randomization process, and I'm going to swap over to Jelena to go through how we assess bias in this domain in ROB2. But I was just wondering before we swap over if there are any questions.
Oh, sorry, I was on mute. We've only got time for a brief. We've only got time for a brief question. We do need to move on, but someone has asked what constitutes an excessive similarity or difference.
Oh, it's a very good question, and it's really hard. I can't give you a hard and fast rule, but it's basically situations which you really think cannot have occurred by chance. So I think we've given a couple of examples where there are massive differences in group sizes, which we don't think are compatible with chance. And I'm sure Yelena is going to go through this in the next section, next section of the session. But that question really becomes important if you think solid methods have been described for the sequence generation and the allocation concealment. So basically, what you're looking for is that situations where solid methods have been described, but that something must have gone wrong during the randomization process, whether it was accidental or whether somebody was trying to manipulate it. So you are looking for large either differences or implausible similarities.
Yeah, I
Okay.
would agree with that. That there is no, again, we can't give you any numbers on that, but if you see there's a relatively small trial and it seems that numbers are equally matched on every single characteristics they measured, that might look a bit suspicious. Doesn't necessarily mean it's impossible by chance, but you might want to delve deeper if you see something like that.